telescoping. They aren't the most convenient because we have to do partial fraction decomposition, much like we did in the previous chapter, in chapter 5. The very beginning of this is to recognize that that factored portion can be torn apart, and that pattern becomes 1 over n minus 1 over n plus 1. So that formula is then in a factored form. Now, one of the problems with this is that as we analyze it, we're not able to substitute infinity. So what we do is we undergo a variable change. We'll let I go from 1 up to n in order to get the nth sum, and later take the limit as n goes to infinity. We now expand this. So the secret to doing these is to write out enough terms to determine what cancels. That's the concept of telescoping. And of course we finish by substituting n in place of I. So writing out some terms, we get 1 over 1 minus 1 over 2. That pair, the sigma says add these together, so we put a plus sign down. 1 over 2. I is 1, so we get 1 over 1 and 1 over 2. Then I is 2, so we get 1 half, minus 1 third. 1 third minus 1 fourth, and so on. Now, where does it end? If we substitute n, we get 1 over n minus 1 over n plus 1. I always prefer to back up and get the term in front of that. The first terms differed by 1. First term here, first term here, first term here. So if I back up by 1, I get 1 over n minus 1. And if I back this up by 1, I get 1 over n. You can think through what cancels and what remains. It should be clear that the halves cancel, the thirds cancel, the fourths would cancel, and in fact everything cancels. Backing up, the 1 over n's cancel, and the 1 over n minus 1 cancels with the 1 in front of that. The only thing left is 1, and the last term, minus 1 over n plus 1. That is the sum of n terms. We wish to find the limit of that as n goes to infinity. So the limit as n goes to infinity of s of n would be the limit as n goes to infinity on 1 minus 1 over n plus 1. This term goes to 0, and it's true that the sum is 1. The telescoping pattern should be expanded. Determine what cancels. Take the limit at the end, and you'll decide on what's the infinite sum adds up to. The challenging piece is that you must undergo partial fraction decomposition to tear that apart. The Harmonic Series is also a famous one. I will summarize what's stated in the lesson. Sometimes our intuition just doesn't tell us what the sum is going to be. Our instincts tell us that this would climb to infinity. 1 plus 1 half plus 1 third. It's always getting bigger, but in fact it is divergent. The sum continues to infinity, and we are not able to find it. It's true that the terms head towards 0, but the sum does not. If you look at the textbook, you'll recognize that what they've done is they've grouped terms. So they grouped 1, 1/2. Actually, the first pair grouped are 1/3 and 1/4. And then the next group that's paired adds up to values that are bigger than 1 plus 1/2. This is bigger than 1/2. And so when we group 2 terms, we group 4 terms, each of the groups end up bigger than 1/2. It does diverge, so it's true that the 1 over n series, which is referred to as the harmonic, does not have a sum, and it is divergent. We can use that in comparing to other series in the future. A theorem that is particularly helpful is referred to as the test for divergence. It comes from Theorem 6, and Theorem 6 basically says that when a series converges, so if you have a series and it converges, we can find its sum. That tells us then that the terms, the pattern of the terms, must head towards 0. Now, when we use that as a test for divergence, we really use the contrapositive. If the terms don't head towards 0, suppose the terms head towards some value like 1, then that sum automatically would diverge. So that is Theorem 7, and it is called the test for divergence. An example of that test for divergence would be 2n over n plus 1 as a series. And even if it's infinite, we should recognize that we can take the nth term and find its limit. You probably recognize that it's going to head toward 2. The limit, as n goes toward infinity, on the nth term formula, 2n over n plus 1, again, we're trying to show that the terms don't head toward 0. We would divide by the highest power of n. So the limit, as n goes toward infinity, on 2 over 1 plus 1 over n is 2 over 1 plus 0. And since the terms do not head towards 0, we should quote the test for divergence. The terms head toward 2, so the sum is divergent.